Hello everyone, welcome once more to another video in our YouTube channel. So in this video we are going to be solving a very technical problem. Yes, the problem is very technical. It's displayed before you and we want to verify the truth value of an inequality. The inequality says that the sum from n equal to 0 to infinity of the ln of 2 all that way to the power n divided by n factorial is greater than 2 and 5. In this video, we are going to verify if this inequality is true or the inequality is false. Alright, so as a routine, you first of all need to try the equation by yourself and then you come and watch the solution to the equation. Alright, so for those of you who are just joining us for the first time, endeavor to subscribe to the channel. After subscription, make sure you turn on your notifications so that whenever videos are uploaded, you always be notified to come and watch. For those of you who have been there with us from the beginning, we thank you very much for your support, sharing the videos with your friends and liking the video, commenting and doing everything possible for the channel to grow. We appreciate you very much for that. Alright, so let's get started. Alright, so first, for us to verify if this inequality is true, what comes to our mind first of all when we see questions like this is to first of all try to see if we can get the exact value of the infinite sum that is on the left hand side of the inequality. If you can get the exact value of that infinite sum, then things become easier. Alright, so first of all, to that infinite sum, I'm seeing a very bizarre number there, which is the ln of 2. So I'm just going to replace it with a certain quantity. I can call it x. We know the value, so it is known. Alright, so it means that that summation of the infinite sum from n equal to 0 right up to infinity, replacing the ln of 2 with x, I've indicated it in red. It means that the sum transforms to the sum from n equal to 0 to infinity of x raised to the power n. Now this is very beautiful because it identifies something that we know, but maybe majority of you don't know. But anyways, let me try to input some terms and we get some few terms of the summation and then we see how it goes. Alright, so when n is 0, the first term will be x raised to the power 0 divided by 0 factorial, right? You get 1 because 0 factorial is 1 and x raised to the power 0 is 1 as well, provided x is not 0. Alright, what about fitting n to be 1? You get x raised to the power 1 divided by 1 factorial. What about fitting n to be 2? You get x raised to the power 2 over 2 factorial, and so on and so forth. So you're summing the terms, right? Because there you have the summation of x raised to the power n divided by n factorial. Now we can clearly see that this identifies the Taylor series expansion of the exponential of x about the neighborhood of 0. We otherwise call it the Maclaurin series expansion of the exponential of x. Now we are going to prove why we can just identify it like that, because maybe most of you will not know what maybe the Taylor series expansion is or what the Maclaurin series expansion is and how to get it. So generally, the Taylor series expansion about the neighborhood of a certain value, let's say x0, is given by f of x. It's actually the expansion of a function about a certain value. So f of x is equal to f of x0 plus x minus x0 over 1 factorial times f prime of x0 plus x minus x0 all squared over 2 factorial times the second derivative of my function and imputing x0 into it, plus x minus x0 all that cube over 3 factorial times the third derivative of my function, imputing x0 into it, and so on and so forth. So it is actually an infinite sum. Alright, so from there, if I replace x0 with 0, it now takes me to what we call the Maclaurin series expansion. But nevertheless, imputing x0 with 0, it means that my f of x becomes f of 0 plus x minus 0 over 1 factorial times f prime of 0, and so on and so forth. Alright, so we can simplify things to having f of x to be f of 0. X minus 0 is x, x on 1 factorial times f prime of 0. plus x minus 0 is x as well, but we need to square and we divide by 2 factorial, and then later we multiply by the second derivative computed at x equal to 0. Alright, so it continues because it is an infinite sum. Now my f of x is any function you see whose variable is x. So what if I now choose my f of x to be equal to e raised to the power x? Like I said, this exact form here is the Taylor series expansion of the exponential function, or at x0 equal to 0, or you can say the Maclaurin series expansion of the exponential function. Alright, so setting my f of x to be e raised to the power x, let's see what we get if we are going to get the exact form. So doing that, we get e raised to the power x to be f of 0 is e raised to the power 0. Now you have your x on 1 factorial. Now what is f prime of 0? To get f prime of 0, we first of all do f prime of x and then we impute 0. But the exponential function has a constant derivative, which is still the exponential function. So the derivative does not change. So derivative of e to the x is e to the x. The second derivative, the third derivative, and so on. So it means that all the derivatives will still give you the exponential function. But now we are not just finding the derivative, we are finding the derivative at x equal to 0. So it means our f of 0 is e raised to the power 0. We have x on 1 factorial. F prime of 0 is e raised to the power 0 as well. F double prime of 0 is e raised to the power 0 as well, because f prime is equal to f double prime equal to f triple prime, which is the same as e raised to the power x. Alright, remember it's an infinite sum. Alright, so simplifying things, e raised to the power 0 is 1. All the e raised to the power 0 gives you 1, and you clearly see the exact form. So the exponential of x is 1 plus x squared on 2 factorial plus x cubed on 3 factorial, and so on and so forth. Alright, so it means that the summation from n equal to 0 right up to infinity of x to the n over n factorial just gives us e raised to the power x. So if I now replace back the x with the ln of 2, it means I'm going to get e raised to the power the ln of the ln of 2. But we know that if I take e raised to the power the ln of a quantity, I'm going to get a quantity. So in this case, my quantity is the ln of 2. So e raised to the power the ln of 2 gives me the ln of 2. So we have succeeded in getting the exact value of our infinite sum, which was very scary at the beginning. So now the question is the ln of 2 greater than 2 on 5? That's what we should be thinking about, because the inequality is trying to say that this infinite sum is greater than 2 on 5, and we are supposed to verify if that is true. Alright, so that's the major question now. Is the ln of 2 greater than 2 on 5? Because we have found out that the infinite sum is just simplifies to the ln of 2. Alright, so let's try to see how we can verify if the ln of 2 is greater than 2 on 5. Now if I use a calculator, right, if I punch the ln of 2, I'm going to get 0.69 approximately, but 2 on 5 will give me 0.4. Even without a calculator, we can do long division or any other method. You are going to get 2 on 5 to be 0.4. But the ln of 2, though, you can find it without a calculator, but preferable, I just prefer to use a calculator and approximate it to decimal places. Alright, so ln of 2 approximates to 0.69 and 2 on 5 approximates to 0.4. So it means actually the ln of 2 is greater than 2 on 5. Sorry, not 3 on 5. So here it's supposed to be 2. So the ln of 2 is actually greater than 2 on 5. Yes. But now what if you're facing a condition where you're not supposed to use a calculator? What are you going to do? So that's what I'm going to be showing you guys, how to compare numbers without using a calculator. So you need to know a little bit of functions and all the rest. Alright, so let's get started with this second part of the proof, meaning proving that the ln of 2 is actually greater than 2 on 5. Alright, so if I want to show that the ln of 2 is greater than 2 on 5, I can multiply both sides by 5. 5 is positive, the inequality sign remains greater than, and I can still show that 5 times the ln of 2 is greater than 2, clearly. So if I am able to show that 5 times the ln of 2 is greater than 2, I have automatically shown that the ln of 2 is greater than 2 on 5, because from this part here I can see divide all through by 5. 5 is positive, so the inequality sign remains greater than. If it was negative, the inequality sign will reverse to less than. Alright, so that's what we need to show. So we are going to use a very important property. if I have a certain number b which is between two other numbers a and c, and then I have a new number which is d and it is less than a, it means that my number which is b is simply greater than z. Why do I say so? Let me try to illustrate why I am saying so. Now I'm just going to consider this part which is saying a is less than b. A less than b, it means that b is greater than a because a is less than b. Now since d is less than a, it means that a is also greater than z, right? So in essence you are saying that b is greater than a and a is greater than z. It therefore means that b is greater than z because the greater than sign is transitive. Yes. Furthermore, you can try to prove that it is a partial order relation. Yes, that's relating two numbers regarding the specifically greater than or equal to. So that works because if b is greater than a and a is greater than z, it means that b is greater than z. You can also verify using numbers. So it means our statement here is correct. So if I just try to look for the boundaries of 5 ln 2, like in this form, and then now I need to compare it with 2, right? So 2 clearly is between the square root of e and e. We know the value of e is an approximate. E is a constant around 2.778 like that, or 2.718. That's the approximate value. So 2 is less than 2.718, and when you take the square root of 2.718, you cannot get 2 again. You get something less than 2. It means that the square root of e is less than 2 and 2 is less than e. Now if I compute the ln on both sides, the square root of e is e raised to the power half. So taking the ln, you take the ln of e raised to the power half. The middle you have the ln of 2, and the upper bound you have the ln of e. Now the ln of e raised to the power half is just half because the half falls down and ln e is 1. Ln 2 remains ln 2 and ln e is 1. Alright, what do I need? I need 5 ln 2. So I multiply all through by 5. Left hand side here, that's the lower bound, we get 5 times 1 on 2 is 5 on 2. The middle we have 5 ln 2, and then the upper bound we have 1 times 5, which is 5. So in conclusion, right, according to our statement that we made here, we said if we have d being less than a, meaning that you have a certain value that is less than the lower bound of my interval, it clearly means that my middle value here is greater than that certain value. So here my lower bound a is simply 5 on 2, and then I can call my d to be 2 because that's what I'm proving, that 5 ln 2 is greater than 2. So since 5 ln 2 is greater than 5 on 2, because my 5 ln 2 is now is actually my my b, right? So 5 ln 2 is greater than 5 on 2 according to this, right? So 5 ln 2 is greater than 5 on 2, and 5 on 2 is greater than 2. So it means that 5 ln 2 is definitely greater than 2 according to our property here. 5 ln 2 being greater than 5 on 2, and 5 on 2 is greater than 2. It means that 5 ln 2 is greater than 2. So dividing both sides by 5, we come back to our proof. So we are going to get ln 2 is greater than 2 divided by 5. So in essence, that scary sum is greater than 2 divided by 5. So the truth value of the inequality is true. Alright, so if you watched till the end, it means you were very patient. Thank you for watching. See you in the next video.